So this is the software interface which we are going to use to control this apparatus, right, and do this experiment. So this is the thing, and I think after playing the video you will understand better. So if you don't understood, please I will ask. I will explain again. Explain it again. So don't worry. So we will play first video. Please listen.
The apparatus which we are going to distinguish the heat conduction of different materials, right? Different.
You can see this is the apparatus, right? Real apparatus. So I took this video. So there are 4 different metal rods, right? And you can see these are the 5 different temperature thermostat sensors, right? So this will be connected in 5 different places, and this apparatus directly connect with this data cable. There's a data cable which connect to the apparatus and the laptop. Then there's a software. Using that software, I already explained that software interface. Using those interface, we are going to control this. We are going to control, or we are going to derive data from using those software.
Metal. So in here we can understand using this apparatus. We are going to distinguish the heat conduction differences between different metal, right? So for your lab sheet you have 4 different metal. One is copper. This one is copper, right? Copper.
You can see the first two rods are copper, and the second two are steel, right? But different kind of steel, and these coppers also different kind of coppers, right? But another two, these two are the aluminum, and other one for the brass, right? So we have done copper, this one, and aluminum one, and brass one, right?
Other one is these two are the copper, these two steel, this is aluminum, this is brass. So here we had to do 4 different materials, but today we are going to do only 3 materials, and we are going to understand how the heat conduction varying according to the metal, right? You should know which heat conduction is high. We are going to do for the copper rod, aluminum rod, and brass, right? So I think you all understood. So this is the apparatus, right? Using this apparatus, this is already connected with the software, right? So using this software we can directly get our observation data, right?
Don't need to think too much. This is just for the easy purpose, right? Easy handling. Thus that apparatus is digitalized, and so we can just control in software interface, right?
So we can see you can see in this software there are 4 in 4 different places, 1 2 3 4. So 5 different places there are 5 different heats, right? Temperature. So those things we can directly obtain from this software, right? So this is the setup here. You can see this.
You can see these are the thermostat props, right? This there's a small holes, right, in every that metal rods, right, which we are going to use here. So in that small holes, we will inject every that prop of this thermostat. So this will detect the temperature of inside temperature of that rod in the exact place. So that hole should be should have the distance of 25 centimeter. Sorry, 25 millimeter. Right, every hole, two holes have distance of 25 millimeter. Right. So when we inject these thermostat props, then it will sense the temperature of that place. Right.
This is a 5 different that 1, 2, 3, 4, 5 different thermostats, right? This is thermostats, right? And if we take that one, first we will do for the copper. You can see.
You can see, right? You can see there are small holes. No? This is to insert this thermostat props, right? Therefore, it will detect the temperature of the that place, right, and that inside temperature of the metal, because the conductivity is happening inside the rod, not outside, right? If it is outside, then it will be convection, right? From the air, we call it as convection, another method of transferring heat. But here we are going to we are testing conduction, heat conduction. That means that should have the direct contact of metal, right? That should be inside of the rod. So we should sense the temperature inside, we should sense the inside temperature of the rod, so that we inject this thermoprop inside, right? But we should make sure, right? We should make sure if there are small holes or anything, we should make sure there is no air, right? We should make sure there should be no air. If there is any air inside this rod, what is happening is there will be heat convection, right? Convection will be happen. So that will be right. That will not be conduction, right? That will then we do not know how this heat flowing heat transfer, convection or conduction, right? We should make sure it will be heat will be transferred only by conduction. So there should not be any air inside these holes, right? Therefore, we inject some the white color paste. You can see, right? Thermal paste. Some of thermal paste we call it as. We inject this thermal paste to make sure there's a conduction with metals, right? There will be no air and there's conduction only, right? To make sure that we are inject some paste, right?
There is a small holes, right? Right. This is to insert this insert this thermostat, right? So that it will this the sensors will be detect the temperature, and we can get the temperature from this software. So here this is the heating controller, right? From here the heat will be produced here, and this will then after fix this one, heat will flow from left side to right side. So there will be a different temperature, and we also know the standard distances and length of this specimen, everything we know. So, and if we know the temperature differences and cross sectional area and length, then we can we have to calculate the yeah heat flow rate of the material. So first we will do for the copper. So here you can see this is one of the
Right. This one is, you can see in this syringe we have white color like liquid, right? Not liquid, it is fluid, have high density, right? So that is that we call it as heat seal. So or thermal paste, right? We should inject to these holes, right? And in one side there's another hole to fix with the heater. So there's also we have to put some heat, this thermal paste, to make sure there is no air inside the holes, and there will be only conduction happening, right? Because we are testing conduction here, right? Conduction, we are going to test the, we are testing conduction, so that we should make sure there will be only conduction inside the rod, right?
One of material to seal the heat flow. Seal the heat flow. I think before specimen explain this copper rod, we have to inject this heat seal, heat material.
You can see this, that is a heater, right? So to fix with this rod, this small bar, there's a hole, right?
Right?
You can see,
Here,
you can see, right?
why you are placing?
You can see this hole now. This hole will be fixed with this part, this shaft with the heater, right? There's a heater. So, but we should make sure somehow we have to apply some thermal paste here, because we should make sure this directly touch with this part, heated part, right? And there is no air. And if there is any air trapped inside, then there will be convection happen. Then we don't know that the data will be wrong, right? So we should make sure there is no air inside this holes, right?
This one is this paste will be make sure that there's a conduction, right? So conduction means there will be a connection, right? Metal connection, right? If there any air trap inside this rod, then there will be convection. There will be convection happen. So then we will get wrong data. So we should make sure that.
I assume that you know that the difference between conduction and convection. I assume you know, right? Because conduction is directly connected, right? And convection means the heat transfer through the air. That will be conduction, right? And convection, that will be convection. Conduction is heat transfer because of the physical contact, right?
Right, every spaces filled with this, filled with this heat seal material, right?
Then after inject this thermal paste, we have to fix, assemble this sample to the apparatus, right?
Now you can see we have fixed this.
Now you can say I have fixed it here. So up to this point, how much length is 100, right? From this point to another, the end of that part is 4 millimeter, 4 centimeter, 4 millimeter, right? This will be another, this part will be 100 millimeter, and every space, in every 25 millimeter, there is a one probe. This is temperature T1, T2, T3, T4, T5, right? So heat flow from here, this part to this part, from this way, right? It will flow this way. So T1 will be higher than this other flow temperature, right? Likewise, temperature will be decreasing, right, throughout this part when the heat is flowing from here to here. So this will be sensed, this sensed temperature will be, we can observe directly using software, right? So, but we know the distance, the temperature, we know the 5 different temperature in this 5 different place of this rod, and we know the diameter of the rod. Diameter is 10 millimeter, and we know the length, different length between these temperatures, we know, right? And using those things, right, the heat, we can calculate the heat flow rate, then we can calculate the heat resistance, right, or thermal conductivity, everything we can calculate, right? But you have to plot the graph, length versus temperature. Length should be x-axis 1, 2, 3, 4, 5, 5 different places. It should be x-axis. Y-axis should be temperature. T1, T2, T3, T4, T4. That will be the temperature curve, right? That we call it as temperature curve. Then you should draw the temperature curve for every metal, right? So see how we can what is the data we are getting for this copper.
Copper rod here. The first specimen is copper. So now we have to switch on this machine. Right, and every control is in our software. So we have to increase the temperature.
You can see here we have to give the maximum temperature, right? Up to which up to how much temperature, up to how much we have to increase, right? The temperature of the heater, right? And this is ambient temperature and heater temperature. Ambient temperature means the environmental temperature, right? The TH1 means the temperature inside the heater, right? So all together here we have 5 different temperature in 5 different places, and inside the heater and outside the environment, right? So there are 7 different temperatures we are going to temperature input we are getting from this software. And here where we apply the heat, right? The percentage of the heat, right? If we increase the percentage 50%, 60%, and 70%, we can give how we can give up to our choice, right? This is our choice. If we give higher percentage, then it will increase quickly. The temperature will be increased very quick. So if we give low percentage of the heat, then the heating ratio, right? The ratio will be low. When it's low, the heating ratio also low, right? And this will be the electrical power, right? Power of the electrical, right? Then when we apply the heat, there will be the electrical current, or electric current will be the source of the heat, right? So that electrical energy will be converted as heat energy. That is happening, right? Then how much electrical energy is that here, right? P electrical, power of the electrical, right? That is the input. Then there are small losses, right? When the electrical energy converted to heat energy, there will be small loss, right? So those things we can get from this. So we'll do it for the copper now, right? Here directly you can observe the temperature, right? 5 different temperature in the 5 different places, right? T1, T2. Then this will be the temperature curve, right? You have to draw this one, right? And here you can directly note down the temperature, right? Everything I have noted down. In that next slide, I will later give you that data, right? Observation data. Then I will show it here and later give to you. Then using those data, you have to plot the graph, right? And you got to analyze which metal is better in thermal conductivity, and how it is vary. You can analyze, right, using this temperature curve.
Here you can play the heat here. So
And
now it is.
you can when we click here, the heating ratio will be increased, right? The heat manipulating variable. That means if it is high, when we give high, the heating ratio, heating speed is high. The heating speed is high. So if you want to heat up quickly, we have to give high percentage of heat, right? Variable.
That heater is
Okay, let's copy the copper.
in this software. using this software, we can see every temperature, that ambient temperature, right? That is that surrounding temperature, and
So
inside that.
now we started, right, directly connected. Now switch on that, we have switch on that apparatus. So that sensor, all sensor will be detect the temperature. Every temperature is 32, 32, 32, 32, right? The ambient temperature 33, that is environmental temperature. And every other temperature is same, because we are not applying heat here yet, right? Therefore every temperature is in room temperature. The ambient temperature also room temperature. There is a small 1 degree difference that you can neglect, right? Then you can assume every is same, because now we have just started. We are not started. We are not switch on the heater, right? So everything here, this is a switch for the heater, right? Everything we can control using this software. Now we have select the material as copper, right? And here you can see they have given lambda, right? Thermal conductivity 380, right? Thermal conductivity is 380, right? The thermal conductivity will be changed according to the that material, right? Copper have higher conductivity, you know, right? Or other than which you will later understood, right? So which metal is better in heat transfer, right? Through conductivity, right? You have to understand. By using looking the temperature graph, temperature curve, you can understand. So every specimen length, everything we have inputted here. The diameter of this rod is 10 millimeter and length is 104. That 4 millimeter inside this heater. So from this one first point to the final point, this length will be 100 millimeter, right? When the heat is, when we apply the heat, this heat will be, that the heater will produce heat, then heat will flow from this side to this side. Then here we will, using this sensor, we can, it will automatically plot the graph.
Both are same now, around there are 1 degree Celsius different inside the heater, right? 32.3, and 5 different places in that hopper rod, right? Our first specimen. Those 5 temperatures are T1, T2, T3, T4, T5, all are same now, 32.1234, right? 32, right? Here where we apply the heat, right? And we should know the difference, that length and everything, right? You can see the total length of this bar is, the copper bar is yeah, 10.4 centimeter or 104 millimeter. Diameter is 10 millimeter, and yeah, that is copper, right? So each, there are the difference between two prop is 25. Part is, right? Yeah, the
Now
inside the
we have
heater,
switch
the
on this
temperature is
heater.
increasing.
You can see the temperature T1 always higher than other temperatures, because this is near, this is the touching point of the heater. Therefore it is always higher than the other four different temperatures, right? You can see the temperature curve, right? This is a temperature curve. This will plot, now it is start to plot the temperature curve.
3.7, like that, right? And that part which is near to the that heater is, heater temperature is high, right? Degree.
So in somewhere, right, from in somewhere we have to take the readings, right? We have to stop and take the reading, then you know the place, right? Then you can plot the temperature curve now. So I just take in one place. So I just take one place, and in that place, using the software also, we can measure the thermal resistance and everything, right? The electrical power and everything we can measure. But you are just asking to draw the temperature curve, no? Then you only need to know the temperatures. That is what, right? That is what you know, what you need to know, temperature and the place, right? So I already marked and type into that observation table, so I will show it later. And here I will point out when it come to 150 or some 15, I stopped and mark it, right? So
we have to wait, and we have to let it be to steady state. So after steady state we will measure. So now
so if we want to be, if we have a lot of time, we can, if you want more accurate, we have to, now it is 150, no? Then it will increase temperature up to 150. Then if we give a lot of time, then there will be steady state. That means then there will be no change in temperature after standard. Then that will be the more accurate one, right?
our temperature is 150. We set it to 150. Take it as right. Right. So here we get one reading, right?
Right. When we expand our graph, you will get another detail of the copper, right? Another detail mean alpha, the resistance, heat resistance, right? And medium temperature. Those things you don't need to know, just for your reference. This is the heat resistance, right? The resistance of heat flow, right? If it is lower, if it is less resistant, that means the the conductivity is high, right? The thermal conductivity and heat resistance will be different, right? Opposite one. If one metal have low resistance, that means it have high thermal conductivity, right? So here we will get heat resistance and power, electrical power, right? This is the temperature curve, right?
For the copper, this temperature. Let's take this as a
I took this as a reading now. Now it is T1 is 115, 108.7, 103.9, like that. I take this as a but as for the to draw the temperature curve, right? So this for your temperature curve, reference for your temperature curve. I already took this, and I will give it to you later. So this electrical power and everything, right? By clicking this part, we will view this one, and using this one you can note it down the electric that the heat resistance and everything, right? And if you want to know, if you want to measure the heat flow rate, you can measure the rate. I think you all know that. If you know the diameter of the rod, and if you know the difference temperature in that between some of the length, right? If we have the temperature in five different places now, and we know the diameter of the rod, we know the length between two places, then you can easily calculate the heat flow rate, right? If you know the heat flow rate, you can calculate the conduction, right? Heat conduction, right? Heat conduction of the copper, right? Or you can calculate the heat resistance of the copper, right? So heat conduction resistance, right? So here this software automatically calculated and gave it to you, right? But we don't need this one, but we can check, right? which have the high resistance and which have the low heat resistance, right? We can check, right? If one metal have low resistance, that means that metal have high conductivity, high thermal conductivity, right? So this is for the copper, right? Likewise, we can observe to other metals. Before that, I will show you the data, right? I will show you that observation data. Then I will like give some explanation in that observation data, and later we will see, play that video, right? Video of the aluminum rod and brass. You can see this is observation data, right? This is a observation table, right? Which is in your lab sheet, right? I think you all refer, but we have done it. We are unable to done for the do for the steel, no. Therefore, I did not have the data for that one, but I have done for these three metal, right? So copper, we have played video, no. You have seen video for the copper, right? This is a recorded temperature of T1 to T5, 115, 108, like that, right? And this is ambient temperature, the environmental temperature, that will not be changed. You can see that is approximately 333 always, right? This is electrical power, that is the power supplied to the heater, right? That is also remain 12.46 or 12 point, approximately 12.4, because this will vary according to the ratio that you saw that H1, that how much percentage heat we are applying. I always applied 50%. Therefore, that heat, the electrical power always same, right? And this is the thermal resistance, right? Thermal resistance, right? Not thermal conductivity, right? Thermal resistance is opposite to the thermal conductivity, right? We call it as alpha, right? And it will we have you notice that we got 65.64 for the copper, and aluminium we have 337.53. That means little high, that thermal resistance is little high. Therefore, you can see when we reach 100, the difference is little higher than the copper. If we subtract the T1 minus T5, here approximately for the copper we approximately have 15, right? 15 degrees Celsius difference across that 100 millimeter difference, 100 millimeter length difference. We have only 15 degrees Celsius difference, but that is for the copper. But aluminium, you can see we have 100 minus 75, 25 degrees Celsius. That means the temperature difference is high, right? Increased than the copper. That means the flow resistance is high. That the thermal conductivity resistance, thermal resistance is higher than the copper. Aluminum have the higher resistance, thermal resistance has than the copper. Therefore, that there is a high difference, right, in temperature changes, right? But same length, right? 100 again, same length, same rods, right? Same length, same diameter in every different metal, right? We are using same size of specimen, right? So therefore, in other case, the brass have higher, again higher thermal resistance than other two metal, right? It is 95, right? The thermal resistance is very high. That means you can notice the temperature difference is more than 40 degrees Celsius. Between that 100 millimeter difference, right? It is the temperature changes is very high. That means the the thermal flow is very low because there is a high resistance, thermal resistance. Therefore, the heat flow is very low, right? That's why it have this much high difference, right? Brass. So this medium temperature, this is you don't need, no. This is the flow rate, the speed of the airflow rate speed. Right? That those things we assume it is zero, right? The environmental, there is the air is the air velocity as we assume it as zero air velocity, right? Those things you don't need to know, and this also you don't need to know. You can I explain it to you for the to better understand about this term of thermal resistance and thermal conductivity, right? To understand those things, I just explain, and this your requirement is to draw the your task to draw the thermal temperature curve. Temperature curve means temperature versus length, right? So we will look that experiment video for the aluminum and brass, right? We'll look for the aluminum.
Okay, now I have assembled that another metal rod which is aluminum.
You can see this specimen have same same size and everything same, right? Diameter, length, and everything same. The every specimen is same, but there is only difference is metal, right? We are changing metal, right? So therefore we can clearly observe the temperature changes, how it is changed, right? But we took this T1 as for the copper. We took I recorded when the T1 is become 115. For another metal, another two metals, I took the data when the T1 reached to 100 degrees Celsius, right?
Rod here I have already assembled. So in here we have to change the metal as aluminum.
Here,
Right,
this is the
aluminum.
input we are going to give to the software, right? We are going to give the that which metal we are going to use, what is this what is that length and diameter of the metal, right? But length and diameter always same, right? When we change the metal, the lambda will be, lambda mean the heat conductivity, right? That will be automatically, the software will assume that lambda has 190, right? If we do not change, then there will be data will be error, because to calculate that heat resistance and everything, that alpha we get alpha, no, using the software. Those that will be the resistance, heat resistance, right? If we do not give that the correct metal, then there will be false in alpha, right? Heat resistance, right? So you can see when it is copper, that lambda, this is uh, heat conductivity. This is heat conductivity, right? That heat conductivity is lower than the aluminum have the lower conductivity. That means high resistance, right? Because copper have the higher conductivity. That is about 300 or something, I think. You can see 300 Copper has 380 thermal conductivity. Copper has high conductivity. Therefore, there is less different temperatures because there is no resistance to flow that flow the heat, flow the temperature from one side to other side. That's why low resistance, lower thermal resistance means higher conductivity, right? Aluminum has the lower conductivity, and brass have less conductivity than aluminum, right? So we'll do it for
So it is temperature difference will be high than the copper, right? You can observe while doing. So now we'll do it again for this. We will apply some heat here. Let's say yeah, 50 again 50.
I applied,
Yeah,
always I applied
yeah. When we
50%. That means therefore that input, that power, electrical power always 12 point something, right? Always same for those three methods.
applying heat, you can see that the temperature is increasing now, right? Inside temperature and every temperature is increasing. But you can look at this graph is different than copper, right? Because copper conductivity of the copper is high, so therefore the temperature difference with the 2 points are low compared to this aluminium. So this graph will be very curved, right? So we will let it T1 become around 100, then we will find out stop we will find out the alpha and everything for that one, right? Note that when it comes to 100, around 100, we have to take this one, right? That heat flow rate and everything. Right?
Right?
Okay, this is your reading. 100, no? Take this down.
Right. This is the reading for the aluminum 100, 89, 81, 76, 75. This is for your temperature curve, right? This is the reading for the temperature curve, right? This will be the temperature curve for your temperature curve for the aluminum to your lab report submission. Okay, so we'll see that thermal resistance, right?
Right?
Alpha.
This is the data for that one, right?
You can see alpha is slightly higher than the copper. The resistance is slightly higher. Therefore, the temperature difference is higher than the copper, right? Copper have 15 degrees Celsius difference between T1 to T5, but this have 25 degrees Celsius difference between T1 to T5. Why? Because it have higher resistance, thermal resistance than copper, right? Okay, or in other words, we can say low thermal conductivity than copper. Okay,
For that temperature, this is the data.
so this is the data for the aluminum. I will look into the data for the we'll look into brass, right? If you want, you can see, right? You can see this is the data, right? Aluminium 73 thermal resistance, right?
Okay, last one, last specimen is
Right. Now, lastly, we are going to do just the brass, right? Brass metal, right? So for this one, we are going to do the same procedure, and you can see this have higher thermal resistance than other two metals, copper and aluminum, right? We have low thermal conductivity than copper and aluminum, or in other words, we can say we have high thermal resistance than copper or aluminum, right? Thermal resistance means it is resist, right? It is blocking the flow of the heat, right? Therefore that is resistant, blocking the flow of the heat, because this part is high heat, no, this part of uh, this metal part will be connected with the heater, so that heater will be producing high heat, so that heat will be flow this part to this part, no. But if there is high resistance, then it will be difficult to follow. Then there will be, you can observe there is a high difference in temperature, right?
Brass, right? So I have fixed brass here, and you can see uh, these 5 different places, and that specimen length and the diameter, everything are same for the everyone, every
And you can see lambda is different than the thermal resistance. This is thermal conductivity, and thermal conductivity is lower than that brass have lower thermal conductivity than aluminum and copper, right? Then brass have lower than this 190, right? We have to change the metal length, material length.
200.
You can say this 120, very low thermal conductivity. That means very high, that it has very high thermal resistance. That's why it have low thermal conductivity, right? We'll do it.
We'll take, okay. Yeah, very low conductivity, I think.
Again,
And
apply heat uh, up to 15%, right?
you should, this is the temperature curve. This is the temperature.
Now you can see there's a big difference, right? Now T1 became 45 degrees Celsius, but there is no changes in T3 and T4.
Curve, right? This part is the temperature curve, right? And this copper, so near to the that heating temperature curve for these different metals in same sheet. That means in the same sheet you have to draw for 3 metals: aluminium, copper, and brass, right? Then you can differentiate, right? By the looking the temperature curve, you can understand, right? Low conductivity or high conductivity, right? So this practical is about distinguish the conductivity, right, of different metal. So now we'll when it reaches 100, we'll say other things, right? So here only you have to understand the temperature curves, so that's doesn't matter. So here where we apply the heat, right? T1 point is near to the that heating apartment, right? Heater. So
This is the
here
T1,
where we apply the heat, so heat will flow here
T1,
to
T2, T3,
here,
T4, T5.
right?
T1, T2, T3, T4, T5. It every two places have, every space have 25 mm difference, right? This is always higher temperature than other four temperatures, right? So our this but from this difference of T1 minus T2, T1 minus T5, we can observe, right, which have high conductivity, which have low conductivity, right?
But inside this rod there's no air, right? Air or anything, right? Therefore we uh, in every part we uh, there's small holes and small holes in one that other side also, right? This side there's a hole, right? uh,
I already explained. Those have filled with the thermal paste, right? Because we should make sure there is only conduction. There will be no convection, right? There will be no air traps inside this rod.
Also, right? Heat seal metal. What we are going to again 100.
So when it
When
reaches
it's the
100,
T1 is
we can
100, that
see
should be the data, right? When it's 100, you have to stop and record for these 5 temperatures. Then only you can plot this temperature curve. Right. Right.
right.
Right.
This is the data, right? This is the data for the temperature curve, right? 100 and 57. You can see 43 degrees difference, right? Between T1 to T15, right? Because it have higher thermal resistance, right? As it has high resistance to thermal conductivity, thermal to flow heat, uh, it have as it have high resistance, that heat will be lost, right? There is high loss, right, compared to other two metals, so that we have a big temperature difference between T1 to T5. So this will be the temperature curve, and you should draw these three temperature curves in same sheet, right? In same sheet. Then only you can um, discuss the results, right? You can discuss how they change. There will be difference in every graph, right? According to the compared by comparing these three the temperature curve, you have to write down the discussion part, right? So
This is your data,
and
and
this will be the temperature curve for the brass, right? So and the alpha will be the thermal resistance is 90,
here this is your
right?
data, right?
Thermal
This is
resistance is 95, 95.4, right? For the brass,
your
right?
alpha.
Very high, right? This will be the um, data, right? You can see now I have played this video for the aluminum and brass, right? You can observe 100 it will change. The T5 will be 75 for the brass. T5 will be 57, right? Why it is very low is because it have high thermal resistance, right? 95, it is higher than the that aluminum and copper's thermal resistance, right? Therefore it have difference, right? Big difference in temperature change, right? So this is your data. So simply you can draw the plot the temperature curve. This is the temperature curve. This is you have to mark 0, 25, 50, 75, 100, right? You can mark the each point, and you can read in y-axis you can mark the temperature, and you can plot the graph, right? But you have to plot the graph um, three different temperature graph in same sheet, right? In one sheet you have to plot the temperature curve for these three different metals, right? And it's better to draw it in different colors, right? If it is red color for the copper, aluminum will be blue, brass will be black, right? Likewise you can draw it. Then for your lab report writing, plot the temperature for the different metals in the same sheet. Discuss the results. You have to discuss the results, right? How the temperature curve will be changing, why it is changing like that, right? Because those have different thermal conductivity, or those have different thermal resistance. Therefore, it changes like that, right? And discuss about the materials used for fins in terms of thermal conductivity, right? fins and in rockets also we call it as seals, right? To prevent the heat conduction, right, from that outside of the rocket to inside, there will be they will use metals which have high resistance, high thermal resistance metals, right? Therefore, heat will not be transferred to the inside of the rocket, right? So like fins also, there will be different metals we are using, because if you take turbines and everything, there will be the temperature will be very high, right? So those metals should not be react under different temperature conditions. Therefore, those metals should have that high resistance, thermal resistance, right? So it will not react, right? So you have to write down these things, and again that same procedure to write down this lab report, theory, procedure, and there is no discussion. So you have to write down the theory, procedure, observation data, and you don't need to write down this part, right? If you want, you can write out. Just write down for these three methods: observation table, theory, this theory, procedure, observation data, and discussion part, right? In the discussion part, you have to plot the graph, discuss the results, and discuss the result of the metals used for fins, right? You can get from internet, right? So this is the end of this practical. I think does anyone have any problem, any doubts or anything, you can just ask now, or you can write down this inbox, and please write down the index number in the chat box, so that I can take it as for the record, right? So please write down your index number in the chat box. So okay, 074, 074, do you hear me? 074,
Yes, sir. Yes, sir.
what is your name?
Prem Ratna.
Sorry?
Prem Ratna.
Kem Ratna. Okay, Kem Ratna, tell me, in the temperature curve, what is in the x-axis, what is in the y-axis?
Temperature in x-axis and temperature in x-axis.
Temperature in x-axis, is that,
Yes,
is that what I told you? Look this slide in temperature curve. Now tell me what is
sir, sorry, sir. Measuring point is
temperature is y-axis. The measuring point, or that axis will be the distance, right? The measured temperature distance. So that measuring point, 5 different points, right? That's the temperature curve, right?
Yes.
Okay, okay. Zero 92. 092. Sugandha Pal, are you there? Zero
Yes.
92.
Yes, sir.
Okay, then do you understood this practical session?
Oh, yes, sir.
Yeah, then what is the objective of this practical, do you think? What we measure here, what we derive here, what we understand here in this session.
Temperature in metallic
Yeah, that
measuring point.
yeah, there's different
I can't explain, sir.
yeah, objective is to distinguish the thermal conductivity, right? Here we study about the thermal conductivity. Thermal conductivity means there will be a heat flow inside the metal, no? In one side, when we introduce heat, if we take one rod, steel rod, if we put that steel rod into the fire or something, then in other part there will be a small temperature increment, right? Increase. Why it is that heat? Because of the heat conduction, right? Throughout this conduction, there will be a heat flow inside the rod, metal rod. That if we introduce heat one side of the rod, then that heat will be flow through this metal to other side. So that will, we call it as heat conductivity, right? That heat conductivity will be changed according to the metals, right? We have we have done for the three different metals: copper, aluminum, brass. Those are three different metals, but we use same size metals as samples, right? We introduce heat one side, and we measure temperature in 5 different places, and look how which have high thermal conductivity. That means which allow high flow rate through that metal rod, which allow high thermal flow, which is not allowing thermal flow, right? If it is high conductivity metal, that means copper, you can see for the reading of the copper, the T1 is 115 and T5 also 100, approximately same. That means it have high conductivity, right? In 0 position also 115 degrees Celsius, and after 10 centimeter, after 100 millimeter from that point also 100 degrees Celsius. That means it have high thermal flow, thermal conductivity. They have high thermal conductivity and low resistance. If it has high resistance, then that will be, the heat flow will be blocked and heat flow will be lessened, and therefore when the heat is flowing, it is difficult to flow, therefore there is less temperature, right? The temperature difference will be high compared to brass. You can see brass have the difference around 43 degrees Celsius, T1 to T5, but copper have only 15 degrees Celsius, because copper have less resistance or high thermal conductivity, but brass have higher resistance and low thermal conductivity, right? So if you have brass, then it is difficult to flow the thermal the heat through this brass metal. It is difficult to flow, but if it is copper, then it is easy to flow that heat will be easily flow from one side to other side through this copper rod, right? So that will be what we are going to study here, right? That we call it as thermal conductivity, right? So our objective is, our practical objective is distinguish mean understand, right? Differentiate how the thermal conductivities of materials different. How this thermal conductivity is changing according to the metals: copper, aluminium, steel, brass. Unfortunately, we couldn't do this for the steel, so we have done for 3 different metals. So how you now understood how this thermal conductivity changing according to the metal, how it is changing copper and aluminium and brass. Out of these 3, copper have high thermal conductivity, therefore it have less temperature difference, right? So this is what we have, what is our objective and what we have done here, right? So this is very important, right? This will be the outcome of this session, right? So let's move to the other one. 38. Zero 53. Are you there? Pasindu.
Yes, sir.
So, so do you understood this practical? You were here, right? Pasindu?
Yes, sir.
So you were here around more than one and a half an hour, right?
Yes, sir.
Okay. Then tell me, out of these 3 metals, which one have lower thermal conductivity? Out of these 3, we have done copper, aluminium, brass, which have low thermal conductivity.
Brass.
Brass, okay. Then which have the high thermal resistance? I am asking you again, Pasindu, which have the you said that brass have a lower thermal conductivity. That is correct. I am asking again, out of these 3 metals, which have
Copper, sir.
high thermal resistance? Thermal resistance.
Copper.
Thermal resistance and thermal conductivity, those are different, right? Those are opposite, right? I already told you. Thermal resistance mean, in that word, in that the term word, you can understand thermal resistance, right? Simply, if we say resistance in electricity, that if it has high resistance, that means low current, no? That means it's difficult to flow the current. Likewise, if it is high thermal resistance, that means that heat flow, it is difficult to flow the heat through that metal. Then the thermal conductivity will be low. Thermal conductivity means the flowing, right? The how fast or how easy to flow the heat through that metal. That will be thermal conductivity, the conduction flow, right? So thermal conductivity and thermal resistance will be opposite, right? So brass have the low thermal conductivity because brass, as it has high thermal resistance. Brass has the high thermal resistance. Therefore, those resistance mean that brass have the blocking, right? It will block the flow of the heat. That's why it have high, as it has high thermal resistance, it have low conductivity or low conduction, right? Low conductive metal, right? In that I already explained. Copper have low resistance, thermal resistance. Therefore, it have high thermal conductivity. Right? Do you understood? Pasindu, do you understood? Or I will explain it again.
Yes, sir. Yes.
Okay, those are two different words, right? You should. It's better to understand. So, 25, 24. Zero 59. Midhusan. Midhusan.
Yes, sir.
What are you doing?
Sir. Sir.
Okay, only 20 people here. So out of those other 7 people will be, I think they don't need this marks for this practical, right? They don't need to do this session. I don't know. No other budgets like you, right? So ask them to at least contact me, right? See what I can do for them. Just these are the easy marks, right? Easy way to getting marks. So if you lose these marks, then it is difficult, right? Difficult to get pass and go pass and get out of this semester, right? So 23 people, 1, 2, 3, 4, 5, 6, 7, 8. Only those who don't write the index number, please write it in the chat box. 2 people did not write it down.
Sir,
Yes.
why we are use the thermal paste in the
Yeah.
practical?
The thermal paste.
It is blue, sir.
Yeah, it is like glue. Not glue, but it is a different paste, right? Made it for that purpose only. That will make sure that there's we are assemble that metal rod into that heater part, and there's a small hole which is to put that insert that thermal prop, no, thermostat prop, no. So those small holes and those things may can have AR, right? AR, or if they don't touch with that metals, right, metal part, then if they don't touch physically, then there will be no conduction. That difference is the conduction and convection difference is the conduction is there will be physical contact. That heat flow should be occur due to the physical contact. So we should make sure there should be physical contact, right? But if we therefore make sure that there will be physical contact and there will be no air trap inside, we are injecting that glue, thermal paste, and after that we are fixing that assemble that metal rod with that heater, and we assemble that the thermostat props. So we can make sure inside that bar and there will be only physical contacts, right? So to make sure that physical contact, only through this physical contact it is flowing through that metal rod, right? So do you understand? Do you understand? Or if you don't understand, I will
Yes, sir. It no trades in the metal.
sorry,
No trade the fix the machine.
I did not understand. No grade mean
Trade
trade mean what is trade?
uh, You can single sir.
again.
පොටෙන්ද සම්බන්ධ කරන්නේ
Grep.
මේ
It will just there's just like I already explained. There's like the hole right in that prop in that metal rod that sample. We have one hole in one side, right? So and in the heater there's a small prop, small shaft like small key, right? So but it is like cylindrical shape key, right? So we can directly inject. Directly it will plug into that heater, right? It will directly touch into that heater. Then from that heater the heat will be produced and it will flow through this metal rod, right? Simply that setup is not complex. Simply you should understand just one side. If this cylindrical rod, right? If it is rod, no metal rod, no, we are one side, we are just introducing heat. We are just producing heat and introducing one side, then let it to flow through this rod, right? The heat flow through this rod and we are measuring temperatures in 5 different places, right? Therefore always T1 greater than T2 and T2 greater than T4, T3 greater than T4, because heat is flowing left side to right side. So there will be no creep or something, just blocked, right? We are just blocking with that heater, the key of the heater, right? So to make sure that you can see just touching the heater, right? By one side, that one side of the metal rod, we are touching the heater, right? The heating part, right? Just assume like that, right? So if you have any doubt, any others? So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. 8. 96. Okay, 20 people. Okay. So is anyone have any clarification, any doubts regarding this session? So I think you all understood. Just right. In your childhood, you maybe understand, right? If one metal part is directly contact with that fire or any flame, in other side or in other end of that metal part maybe have some the temperature difference, right? When you touch the other part of the metal, you will feel, right, that temperature, right, suddenly. So that due to the conduction, thermal conductivity, right? That will change according to the metals, right? That is what we are measuring, what we try to understand during this session, right? If anyone have any clarification, please ask. You have 10 minutes to ask. And so I think you all clear of writing lab reports, theory, procedure, graphs, and there's to discuss the graph, and there's other question, right? Discussion part. That will be the lab report submission, right? And again, you have same due date and period for the submission and everything. So, and if you have any clarification or anything, please contact me. And you have last practical, the 7th practical next Monday, same time. So before that, it is better to contact. If you have any clarification regarding the previous practicals, or if you do not attend that the previous practical, please contact me and talk to me. So ask others to do that. So I don't like to lose someone marks for no reasons, right? So these are the these marks must, right? So you know that if you don't physically, if you don't when we are doing the practical, if you don't attend the practical, you can sit for the end exam, right? That's because it is very important. But we are, as we are having practical in online, it is difficult to say like that. But if we have, when we conducting physically, practical is very important. If you don't participate in practical, then you can't sit for the exam, right? So that's how much, that is how important this practical session. So so that's it. I think you all understood. So we will wind up this session here. So you all are clear with this session, and see you in the next practical. So thank you for participating in this practical, and see you next week. Bye.
Thank you.